Welcome to the course on VLSI physical design with timing analysis. In this lecture, we will discuss about mean cut placement algorithms. So, the content of this lecture includes basically first of all we will discuss about the routing congestion, then we will discuss the mean cut placement algorithm. So, what is the mean cut placement algorithm? There are two popular mean cut placement algorithm which is extensively used. One is the mean cut placement algorithm using the Kerninghan-Lin algorithm, and the second one is basically the FM algorithm. So, what is the routing congestion? This plays a very vital role because whenever you do any kind of VLSI chip design or something, we cannot route our design. So, we should understand why it is not routable. Okay. So, this here we will discuss why a net is not routable, reason behind it. So, before going to that one, we will discuss about two things. One is called the channel, CH stands for channel, and the SB stands for the switch box. So, whenever we have only path from basically two sides, path from two sides. See, if you can see here that the net can go this direction or net can move in this direction, but vertical nets cannot be routed. So, this is called your CH or the channel. But in case of switch box, you have routing possible in this direction as well as this direction, vertical direction as well as in the horizontal direction. So, this is called switch box. So, what is basically happening is that we have a ratio of the demand of the routing track to the supply available in the routing track. So, we have a requirement of how many signal I can route, and there is what is the availability of the routing tracks. So, based on that we can define a routing congestion factor. So, this routing congestion is estimated by number of nets thus pass through a boundary of a individual routing region. Whenever I have this switch box or the channel, these are the routing regions. So, here how many nets can be routed? So, that is fixed, and so once that is fixed, then we can utilize that resources. Okay, we can utilize that resources. So, formally the local wear density, the phi of P of E of an edge E, basically we have a edge E between two neighboring grids is denoted by, this is phi of P is equals to eta of P of E, eta of P of E by sigma of P of E. What is eta of P of E is the estimated number of nets that cross E. Okay, that estimated number of nets that cross E. Now, sigma of E is basically maximum number of nets that can cross. Okay. So, that maximum number of net is basically the provided by the resource available to us, and estimated is the what we are doing the routing. So, the wire density of a placement is phi of P is basically the maximum E belongs to E for all edges. Okay. I am finding phi of P of E, then what is the maximum of that one I am finding, and this E is basically set of all edges. Okay. And I am finding, so this small, this is basically the lower case phi of P of E is for each edges, and the upper case phi, so it is for each edge, uppercase phi is for maximum of, uppercase phi of P is maximum of all the edges. So, we are worried about all the edge maximum value, not worried about individual edges. So, if my phi of P is less than 1, then design there is no issue, your design is fully routable. If phi of P is greater than 1, means we have more demand, we have less supply. more requirement of routing, but there is less resource available. In that case, your design is not routable. What you have to do? We need to change the nets. Deter means change the nets through the less congested area. Let us say if I going in a car, my car is in a congested area, I need to go in a less congested area such that I can reach the destination. The same method is applicable here. If some path is congested, I need to change my direction to a less congested edges such that I can route that net. So, the congestion driven placement seeks to minimize the phi of p. Whenever I have basically congestion driven placement, I am trying to minimize the phi of p such that all my nets should be routable. So, basically this is the main concept of routing congestion. So, let us take an example to understand this concept. So, we have a wear density, we need to find out the wear density of a placement. So, these are the parameters given to us: number of nets, the number of vertical cut line, horizontal cut line, then sigma of E of 3 for all local cut lines, and I have all the nets N1, N2 and N3 is given to me. Now, I need to find out my wear density phi of p and determine whether my all the nets are routable or not. So, first of all I will find out eta of p of h 1. Okay. So, eta of p of h 1 is basically this one. So, this is 1 here. Okay. So, this in this cut I have 1 here. So, this one is 1. Now basically eta of V 1, eta of V 1 is this one. So, this is also 1 here because I have only one cut. Now, I will take one more example, let us say V 6. Whenever I have V 6, this is my V 6. Okay. So, there is no cut. Okay. So, this is 0. Similarly, you can calculate for all other cuts. Now, what is the maximum eta of E? Maximum eta of E is basically, if I can see here, this is the thing and this is the thing. Okay. These two are the maximum eta. So, the maximum eta of E is 2, then I have the sigma, basically I need to find out the phi of p. Okay. The phi of p is basically eta of p of E by sigma of p of E, which is basically 2 and the number of routing track available is 3. So, it is 2 by 3 and your phi of p is less than 1, 2 by 3 is less than 1, hence the p is the placement is routable, hence the placement is routable. So, we will discuss about some placement algorithms. So, min cut is one of the popular placement algorithm. So, what is the input to the min cut placement algorithm is the netlist, okay, and the layout region. So, what it does is that it divides the overall layout region into smaller and sub netlist and sub regions. Okay. So, we are dividing the overall design into smaller designs. Okay. So, the process is carried out till each sub circuit. Okay. What is happening in this placement versus the partitioning? Whenever we are doing partitioning, we do the partition and we have created 2 different partitions. But in this case, we repeated that partitioning till each sub circuit will occupy a space in the layout, means each single gate will get a location in the layout, unique location in the layout. So, each logic gate will find out its unique place in the layout. So, the min cut placement algorithm finds the unique place for each logic gate in the design. So, this is the main theme of this min cut placement algorithm. So, there are basically it all depends upon a heuristic. So, we each cut heuristically minimizes the number of cut nets. So, there are two popular algorithms there, KL and FM, but we discuss in case of partitioning. The same algorithm can be exploited to do the min placement of the logic gates. So, we will discuss the KL, then the FM algorithm. So, here what is the this min cut placement algorithm? So, what are the inputs to the min cut placement algorithm? We have a netlist and we have a layout area. Okay. We have netlist is given to us, we have a layout area given to us. So, what basically the minimum cell, minimum number of cells for a region is cell underscore min. So, that is also given to us. So, what is the final output? These are the inputs and final output is my placement of all the logic gates in the in that area. So, what is happening here is that initially there is nothing is there. So, the P is phi. Then what we are doing? We have a assign netlist and the layout is given to that one. So, we are assign the netlist to a layout area. So, we created a variable regions here. We operate this flow till this one runs for one time, till this one is the run for one time. After this there is a while loop which will be repeated. So, when it will stop? When there is no element in the regions. So, we have some element in the regions, then we are basically processing that one. So, first we will take this is regions, remember S is there, so this S is there. Then we take one element from that regions to that is called region. Okay. Now, what we are doing? Since I have taken that one, I want to remove that first element from the set. So, I am removing the that region, the first element from the regions, because I want to process that. Now, what we are doing is that we will do the bisection. We basically region contains more than cell underscore min cell. So, if the region which is the element we found out, if it is contained more than cell underscore min cell, a minimum cell what is given in the algorithm, then what we have to do? We bisect the region into two part, that is SR1, SR2, two part, we divide that into two part. Then what we are doing? Now, we are adding that one SR1 to the region, the original set. Now, we are adding SR1 to the original set. Okay. Now, the which is the first element? SR1 is the first element. So, now now in the region set I have two elements. The first element is SR1. After executing this statement, after executing the second statement, I have SR2. I have SR2. Now, what is happening is that now we have subblocks. These are subblocks because I have already done the bisection on that one original region. These are having less elements in the inside that. Then what we are going? We will repeat this thing, because we will repeat these things till the region is empty. When we are repeating this one till it will reach the minimum cell area, minimum cell what is defined in the algorithm, then we will place that one. Okay. Place and place the region. Then what we are doing? We are adding the region to the P. So, in this case what we have to do is that once SR1 is processed, then this placement of the SR1 and each of these things will be done, then we will go to SR2 block and do the same thing again. So, this is the min cut placement algorithm, but in case of a partitioning algorithm, we do this bisection for one time. So, basically here we have alternately applying the cut line directions and repeating the cut line directions. So, the algorithm divides the layout by switching the between the set of vertical and horizontal cut lines. Basically, it switches between horizontal and vertical cut lines. So, once it is do it for a vertical cut, in the next time it will go for a horizontal cut. Then finally, once all the cells are placed, then it will terminate. Okay. So, the first time let us say if it is horizontal, next time vertical, then again horizontal, then vertical, like that it will repeat. It is very useful for standard cell based design with high wire density in the center of the layout region. It is very useful for the standard cell based design methodology. So, this is the basically actual layout area. First we do a horizontal cut line. So, this is one horizontal cut line. Now, we have two vertical cut lines, from here to here is one and here to here is the second one, from here to here is the second one. Now, we have 4 horizontal cuts. Okay. This is one horizontal cut from here to here, this is 2 horizontal cut from here to here, this is 3 horizontal cut from here to here, this is the 4 horizontal cut from here to here. So, this process will repeat it. Okay. So, we are basically repeating the cut line directions. The layout is basically completely divided or divided using only the horizontal and vertical cut line until each column or a row is the width and height of a standard cell. This is very important. So, finally, what we will do, one of the column or a row will have either one standard cell, width and height of the fit to the width and height of the standard cell. So, the layout is divided using the orthogonal set of the cut lines. The layout is divided repeatedly into set of cut lines actually, which is orthogonal, and it often results in a greater wall length because aspect ratio of the sub regions can vary from 1. Now, we are discussing how we can do min cut placement using our KL algorithm. Okay. So, the KL is a popular algorithm. So, we will discuss how we can do the placement using the KL algorithm. So, we have 6 gates are there. Our layout area is 2 cross 4 and initial cut is this is our initial cut. Okay. Since I have basically 4 cross 2 placement area is available. So, I have basically 8 elements need to be placed. However, we have basically 6 gates are there in the circuit. So, what we are doing is that to find a placement with minimum wire length using the alternate cut line direction and using the KL algorithm. So, what we are doing here is that we are converting the basically our netlist into a graph. So, this is the basically node corresponds to this one logic gate 1. Similarly, this is corresponding to node corresponding to this gate. So, now this is the first cut. Okay. And if you can see here whatever I told you, you have 2 cross 4, 8 placement region is available, but we have 6 logic gates are there. So, we need to add basically 2 extra node to the graph. These 2 extra nodes are added and basically there is no connection, but these 2 extra nodes are added to the graph. Now, what we are doing? We are finding the if I have this cut 1, then what is the gain? So, left hand side this is the left hand side, this is the right hand side. Left hand side is basically having A, B, C because this 1, 2, 3 corresponds to A, B, C and basically this is 1, 2, 3 and D, E, F is basically 4, 5 and 6. So, now what I am finding is your D of B, whatever I discussed in partitioning. D of B is basically E C of B minus E of N C of B. What it is doing is that how many nets are cut by the cut line minus how many nets are not cut by the cut line. Let us say I have this cut line is there. Okay. So, the node 1, let us consider the node 1. How many cut by the cut line is 1, this is 1 and what is not cut by the cut line? There is no edge which is not cut by the cut line. So, this is 0. So, D of 1 is basically 1, D of 1 is basically 1. So, similarly, you can do it for other, but then there is a gain formula what we again discussed in the KL algorithm. Delta G of A comma B is basically D of A plus D of B minus 2 C A comma B. Okay. So, basically, so this formula is used to find delta G of 1, which is 2. So, the 2 which is having the highest gain is basically node 3 and 4. So, what we can do here is ideally we need to find for all combination of delta G, but because of time we are just showing it for one delta G, and which is giving you the maximum gain. So, then we can swap node 3 and 4. So, 3 will go to this partition and 4 will come to this partition. So, now if I do this swap, then my new cut line will be look like this 1 4 2 in the left hand side and 3 5 6 in the right hand side. So, again we are not going to the full cut lines. Now, we are considering in the basically left hand side only or right hand side only. So, here what we are doing, the cut 2L, because it is a left hand side and the second cut. So, if I do that cut, then I have a top is having 1 comma 4, bottom is having 2 comma 0, and similarly I have cut 2R. Okay. So, here top is having 3 comma 5 and the bottom is having 6 comma 0. Now, what we are doing here is that here we are again finding the for d of 1, d of 2, d of 4, d of 0, like we did for the KL algorithm in the partitioning algorithm. So, here then we found out no delta G is greater than 0, hence there is no swapping of the nodes possible here. So, we can repeat the same thing, no swapping for the other case also, cut 2, there is no swapping possible because no gain in delta G, no delta G is greater than 0 here. Then we will repeat for the same procedure for cut 3 TL, cut 3 TR, cut 3 BL, cut 3 BR. So, T stands for top, I can write here T stands for top and B stands for bottom, L stands for left and R stands for right. So, these notations are used to individually cut each of the sub units such that each basically location will assign one block. Each region has one node, each region has one node. So, after it all the node each gate logic gate is assigned one node, then you can terminate the algorithm. So, this is the final placement and so this is in the graphical domain and this is the actual placement of the algorithm, So, this is using the min cut placement using the KL algorithm. So, now we will discuss the min cut placement algorithm using the FM algorithm. Okay. So, what is given here? The circuits with gates A to G, then the ratio factor, then the gates area of each of the gates, okay, and the initial partition, then the fifth one, of course, the layout area. So, here what is the target is to how we can place all the gates in that 2x4 layout. So, we need to find a placement with minimum over length such that we can use the two concept here. One is the alternate cut line direction. First we will do a horizontal cut, then we will do a vertical cut, again we will do the horizontal cut, then we will do a vertical cut like that, and then we will exploit the FM algorithm here. So, this is the layout area. So, first vertical cut is basically this cut 1, okay, This cot 1 you have L equal to A B C and means left hand side is A B C and right hand side is D E F G. Okay, D E F G. Then what you have to do, we need to find out a balance criteria. Okay, the balance criteria is basically area of A should be less than equals to the ratio factor area of A of partition A. Let us say the total area is denoted by AT. So, ratio factor multiplied by AT minus the maximum size gate, logic gate, max of let us say the gate, logic gate AG should be less than equals to. So, R multiplied by AT plus max of AG. So, the max of AG in this case, if you can see which is the max of AG here, NAND and NOR gate, which is having the maximum 2. So, here max of AG equals to 2 and total area AT is 11 and ratio factor R. So, this is given, this is one parameter, this is second parameter and the third parameter is your ratio factor R, which is 0.5. So, after we do this, we have area of the partition is bounded by 3.5 and 7.5. Okay. Area of the partition should be bounded by this much. Now, we will find out in case of FM algorithm, we need to find out our gain. So, for finding the gain actually, we have a formula is that delta G. Okay. Delta G of a node is basically Fs of C, okay, minus T of C. Okay. So, this Fs of C is what? Fs of C is basically is the number of nets is number of nets connected to C, but not connected to any other node, any other cells within C's partition, okay. Correct. So, this is Fs of C. Then T of C, this T of C is basically the T of C is basically uncut nets connected to C. So, for example, if you can see here for let us say the node D. Node D, if I go by node D, basically node D is connected to this cut by the cut line is 1. So, the Fs of C is 1 for node D, okay. And T of D is basically 1 because this net is not cut by the cut line, okay, uncut nets. So, this T of D is 1. So, the gain of moving the D to the other side is 0 because 1 is, if I take the D to the other part, then my gain will be 0 because it has one cut net that will be reduced and another cut net will be created. So, in this method we will calculate all the delta G's. Then after I found the delta G, then I have to see which is having maximum gain. A, B, C and G is having the maximum gain. Then I need to check my balance criteria. Then in this first case A, the balance criteria is violated. Okay. So, I cannot do the movement of A. In case of B, the balance criteria is violated. So, B cannot be moved to the other partition. In case of C, the balance criteria is violated. So, it cannot be moved to the A partition. Then in case of G, the balance criteria is maintained because the 6 is basically the area of A is become 6, which is bounded by 3.5 and 7.5, and it is satisfying the balance criteria, and G can be moved to the other partition. So, G can be moved to the other partition. Now, the new partition will look like this. Now, the new partition will look like this. Earlier I have 3 cuts, now it is becomes 2 cuts. Earlier I have 3 cuts, 1, 2, 3, now I have only 2 cuts. This is 1 cut and this is the second cut. This is the 1 cut and this is the second cut. Hence, the number of cut is reduced by 1. Similarly, I can do for the second iteration. So, this is the gain which is having the highest gain, then the balance criteria is satisfied here for the node A. So, this is the new partition. Okay. So, this is my new partition. So, I have number of cut earlier is basically if I can see here earlier this is 1 and 2. Now, after doing the partition I have only 1 cut. So, number of cut is reduced by moving the A to the other partition. I have number of cut becomes 1, number of cut is becomes 1. So, this process will be repeated till all the gates will be assigned to each of the locations, and this is the final placement using the FM algorithm. So, in this lecture we discussed about the routing congestion first, then we discussed about 2 min cut placement algorithm such as KL and FM algorithm, which is very useful to find the location of the logic gates or the standard cells in the final placement. Thank you for your attention.